Cool. So the next sort of intro talk is the last major drug design sort of conversation we'll have. Tutorial 7 is now up on GitHub. This is the second to last tutorial overall. And so in tutorial 6, we learned a little bit more about the add medchem mutate, specifically using it in multiple places on a molecule in combination with protein design, with some special care taken to try to preserve chirality. In this tutorial, we're going to focus a little bit on the ring swap mutate. We're also going to look at one more example of a special behavior of the add medchem mutate. And so let's go ahead and get started. I'm going to share my screen again and going to, I think I'll start with add medchem, just that way it's sort of consistent with the mutate you're interested in before, or that you're currently working on, before we switch gears to ring swap. So let's go. Yeah, all right. So I am now in the tutorial 7 directory in the input ligands made on demand style. So this is, if you recall from a few tutorials ago, I had that diagram where I showed sort of the framework for the reaction-based drug design, juxtaposed with the alchemical framework for drug design in the BCL. And there was a little bit of overlap with two mutates in the alchemical framework. One of them was React, which naturally borrows code from the reaction framework. And then the other one was add medchem. And you have now used add medchem multiple times to append these sort of pre-generated functional groups to your molecule. And really this, when I originally made add medchem, my thought was, I don't want to have to use alchemy or extend with linker or do weird, like sort of successive moves too much. I would like to be able to create libraries of molecular fragments that I can recombine, because that's, I think, how a lot of people think about drug discovery. Like, oh, I want a tert-butyl or a trifluoromethyl over here, or oh, I really need something that's got more dipoles over there, or something that's going to form a hydrogen bond over here. And so instead of having to build those up from single atoms, it made sense to have a way of adding these in chunks. But at the same time, we wanted to make sure that you weren't adding the wrong part of the molecule together, right? So like if you want to add, with ring swap, we have a lot of freedom with respect to how we connect the rings. With add medchem, we're restricted because we define, and actually if I skip over to tutorial 6, just briefly, and I go to the bump medchem fragments, and we look at these molecules. So these are the fragments that you can add for a particular location, right? And you can't attach at this atom, because what add medchem is doing is looking for this atom. And the way that it knows to look for this atom is it is marked with an X in the SD file. So if you were to actually look at any of these compounds, we could see that one of these is an X. Now there is no periodic table of element thing that is X. There's Xe for xenon, but there's no X. And so that actually represents an undefined atom type in the BCL. Undefined element, undefined atom, undefined. But we can use those strategically. It doesn't crash out. It doesn't prevent us from doing it. If you try to generate a 3D conformer of something that has undefined atoms, that won't work because there are no statistics on how undefined atoms are involved in dihedrals. But if you just want to load a molecule that has an undefined atom, that's fine. And so if we look at this, and I'll make this bigger so you guys can see. If we look at add medchem, there's a bunch of options like you're used to. Mutable elements are elements typically in the molecule that you say I'm allowed to use in an input file that can be mutated. But add medchem always takes this medchem library, and those molecules will not attach to your input file unless they have an undefined atom type, because that's sort of the attachment site. So interestingly, this is sort of just very close to how a lot of people do these one-shot or made-on-demand type reactions. The only difference is, in that case, you have two fragments, where on each fragment you have sort of a dummy atom, and you're just saying, I'm going to connect the two fragments via that dummy atom. And so if we go back over to here, for example, if you take an amine and you take an acid, and let's just take a look at these in Pymol. And so this is what they look like. This is our amino group right here. And so we have the nitrogen, and then this is an X. Different databases will use different atoms. I've seen selenium used. I've seen palladium used. So whether you're looking at Mo and their fragment library, whether you're looking at enamine and the fragments you can download from them for their made-on-demand stuff, this type of formatting is very common. And so you can say like, okay, well, if I have an amine and I have a paired database, a database that is supposed to go along with this, in this case, an acid, I've also got an undefined linkage right here. And so you can say in the add medchem mutate, hey, I can pass, let's say I'll pass the acid as my medchem library fragment. So it's going to look for this atom. If in your input files you specify that the only mutable atoms, the only things that you're allowed to potentially modify are an element of type X, it's going to say, oh, only modify undefined element types. And by doing this, you can effectively achieve the same type of linking together that you get with these one-shot type reactions. Then that is just a more, sort of specific use case of the behavior that already exists, because we can say, oh, I only want to set to mutable my carbon atoms. And then it'll say like, okay, well, all the atoms indices that are carbon, let's collect those. And then we'll randomly pick from that pile of atoms when we go to perform a mutate, whatever it is. And so this is just saying, well, why don't we set that to be undefined? So only choose the undefined element type. And then you've also got a medchem library that by definition requires an undefined atom type, and it puts them together. And so what does this look like? I ran this command earlier, but we can run it again. And I'll remove my log file on this. So molecule mutate, input file names, acid, output, amide product, acid, and it's going to use add medchem, and I'm going to pass my amide. The key here is setting mutable elements to X, and so that says only do the undefined. And then it's going to go ahead and run. And then I've got my product out. And so now we've got a nice linkage between these two things in three-dimensional space. I forget which argument. I guess we put the amide first. Is that right? Acid first, and the input file name was what? The acid. And so the reason why that matters is because if you recall, we try to save the coordinate space of whatever our input file was. So if this was our input file and our library fragment was the amide, then the space that we preserve is the input file. And so as part of the exercise in tutorial 7, you're going to do this from both directions. You're going to start with an amide or you're going to start with an acid. And you'll see that depending on which fragment you start with, those are the coordinates that you keep. And to Georg's point, maybe we do want to be able to sample everything. And so that's a feature request we can definitely add where we add another mover. So let's say you get this out as your product and you want to sample all the degrees of freedom for the conformer or a different subset. We can apply then maybe a subsequent mover that will assign new rotamers to the small molecule for whatever following relaxed step you do. That would be pretty easy, I think, actually. So yeah, so that's it. And so what I've done is I've actually provided a small set of things that you can use. So I've got 2,914 amines, and I've got 451 acids. And so you guys can also try out just making different products, seeing if you can design a protocol to link these fragments together inside of a binding pocket. So what do you have to do to then relax the resultant compound in Rosetta, et cetera. And so that'll be part of this tutorial. I'm gonna switch gears to the ring swap unless anybody has any questions on that. Going once.
Ben, just one question. Is there any way to, so does this connection can produce both cis and trans amide bonds?
So the amide bond that will be formed is going to be generated with BCL conf. And so the conformer generator, because half of it, is yeah. I haven't actually tried seeing, like, can we define the reaction in a way that will specifically favor one, but you're almost certainly going to get a trans amide for everything, because getting a cis amide is much less likely in the BCL conformer generator.
Okay.
Yeah, not impossible, but I wonder if we could design it all sneaky like, so that way it will, in one of the earlier tutorials, I showed that you can control the directionality of how you add substituents based on which hydrogen atom you remove when you open the valences. I think that was tutorial 5. And so maybe we could design the input files to do something similar here, but, or maybe even easier. Well, we'd have to make an amide specific flag. Let's chat about that, but I think we could do something for you. Good idea, good question.
Okay.
Other thoughts? All right, cool. So let's go ahead and switch over to, oh man. Let's do, there's also a fun example where I show you how to build a molecule from nothing, or not from nothing, but from another one. We use a couple extra mutates. So if you get to the optional section on building, I'm testing the selectivity of 2 very, very, very similar compounds for the receptors. Pay special attention to how we build molecule 002. But that's all in the tutorial. Yeah, so let's go to Affinity Design real quick. So you guys are going to do both Affinity Design and Selectivity Design. The selectivity component of this tutorial is primarily how to be very creative with filters to get what you want, as well as with the packer and the sequence threader to change the sequence of the proteins. But part of the optimization of the molecules involves changing core structures in the ring. And so I want to pull up this. This is a compound that was published by Craig Lindsley's lab by a fellow named Dan Jeffries, who is a medicinal chemist who I worked with very briefly, but he's a very nice guy. He's a very good medicinal chemist. He did a series of compounds based on this scaffold with this difluoro group right here. And so you're going to work with this scaffold a little bit today. I got the citation too, so you can read about some of this R that he discovered. This is already docked and ready to go for you guys. But the important thing is to think about the problem of swapping rings. And so we have this mutate called ring swap. And with that mutate, you basically are just taking a ring from a database and you're plugging it into your molecule. And that turns out to not be trivial to do if you want to keep your molecule mostly where it is. It is not hard to do it over here on a terminal ring, over here on a terminal ring, because there's no downstream propagation. There's no lever arm effect, effectively, of sampling dihedrals for those, because these are the most terminal parts. So you're really just sampling whatever the new sort of conformer will be for that ring if you attach them. But it's a little bit more challenging when you're trying to sample the core part of a ring. How do you minimize those downstream propagation effects? Another issue we run into is when you've got a core that doesn't just have one attachment site. What if I were to try to substitute in a 5-membered ring here instead of a 6-membered ring, or something else that had some different ability to substitute? Would I end up with a different geometry? Would I even be able to connect all my fragments back, or all my substituents back to that core? So how do we handle the case where we've got just very different topology rings that are being connected? And there's a few different ways that we go about doing this, and we go through it in great detail in the tutorial because it's important. And so think about these problems, but I'll start a little bit here. One of the things that we talked about was substructure matching. Yeah, let's do could have substituents. And I'll show you some of these. So could have substituents. So I did a number of ring swaps, and you can see sort of what the result of these ring swaps are. I've got very, very different rings that I'm putting in here, but it's doing its best to maintain the overall topology or binding pose of the molecule. It's not always giving us, well, in fairness, we don't always know what rings are going to work out or not. But notice that I'm able to make all of these connections. I'm actually still being able to keep these. I just did random sampling of rings. And so we talked about substructure comparisons earlier in the context of doing alignments. But we can also do substructure comparisons when we're just thinking about how do we attach things together. And so one of the options for the ring swap is related to how do we actually decide when we're comparing the rings that we're going to swap in, whether or not they or how they should be oriented with respect to the old ring. What we have is a type of atom or node comparison that will check to see whether or not the two atoms are able to make the same number of substitutions. So could have substituents. By doing this, you can try to arrange your rings with respect to one another so that way atoms on your new ring that are able to be substituted in the same way as atoms on your old ring are put in the same place. This allows you to reconnect your molecules as close to sort of the original geometry as you can allow, obviously minus some refinement. But that's what these things are about. So we have these options, atom comparison, which you've seen several different places before, and bond comparison. We also have these types of comparisons when we're talking about the mutable atoms, but these are separate for the fixed and mutable atoms. And so what it's saying is I'm going to go ahead and choose a new ring from my ring library. I can either, if I just leave it on the very default settings, the super most default settings, it will just take that ring and it will throw it in my molecule and it will randomly reattach all the substituents, which is really good for like ligand-based design, but really bad for structure-based design. And so for structure-based design, we can say that we want to be conservative. And so what this option does, as it says right here, is it aligns a new ring to the current ring prior to substitution, because we're trying to essentially keep the right shape of our molecule in the binding pocket. When it's doing that alignment, when it's determining, well, how is it going to align the current ring to it? It's going to be a substructure-based alignment, but what determines the substructure comparisons? And so a part of this tutorial is comparing what happens if you could have substituents to element type, to atom type. You can also go through chirality and all the other atom types there are there. But what I wanted to show you is that when you check to make sure that you can actually have substituents, your rings pretty much, look at these, they all line up again. I'm swapping out rings, but the molecules are pretty much staying where they're supposed to be, where the original molecule sat. In contrast, if I'm aligning based on atom types or element types, you're going to find that sometimes I'm not actually even able to complete my molecule. Sometimes I can't attach all the substituents. Sometimes I can, though. It's not all the way bad. Oh, is this too optimistic? Oh, wait, I should do element type. Hold on, bear with me. Maybe atom type, because it's got the hybridization information as here. Okay, so here's an example where what happened was when I tried to swap out the ring to replace it with something else, I was left with a new ring that was unable to make an attachment to that other part of our molecule. And what happens is that if we can't attach something, we don't. So you end up truncating the molecule and making it too small. You can always add filters to filter out molecule substitutions that are too small. But you want to be careful during this, that you're not wasting too many iterations on designs that doesn't work for. One thing I do notice, though, that's nice about the element type and the atom types is you oftentimes get this protonated nitrogen more in the right place. So something that may be worth experimenting with is doing multiple different types of ring substitutions to try to make sure that, oh, hey, if I take the same set of rings, but I align them in different ways to my starting point, I may actually get different combinations of molecules, some of which may be useful that I might not have expected. So, but that's the idea. We can also do something called refine the alignment, where after you swap in the ring, if it's a really dramatic perturbation, you can also do like a small property-based alignment that's pretty quick to refine the position of the whole molecule. So then that alignment will happen on top of the other just ring alignment. And if this seems a little bit abstract at the moment, just wait till you get into the tutorial. The tutorial will walk you through this whole sort of procedure in a lot more detail. But yeah, so those are the two main takeaways from tutorial 7 with respect to how you do the alchemical transformations. With AddMedChem, if you set the mutable elements to only be the undefined elements, and you pass a MedChem fragment library that corresponds to an actual sort of coupled reaction, you can do Suzuki couplings or Hammond couplings, whatever other type of reaction you can find in a lot of these on-demand libraries. The other thing is just that we're going to go into a lot more detail on how to use ring swap, which I hope also just gets you thinking about how you might consider handling some of the other aggressive mutate options when you're doing dark design. I don't think Hope is on this chat, but I was hoping she would see all the dramatic ways we can do the rings, because the first time I gave a talk in Meiler Lab, I just did like halogen substitutions or something, and she was like, oh man, small molecule drug design, they only change like tiny things. That's not cool. But I shouldn't give her too hard of a time because she's not here. So anyway, I'm just having fun. So yeah, anybody have any questions, or are we good? I'm happy to chat about this.